Yeah. So thank you for coming to this presentation about ORTools and MathOptInterface in Julia. So MathOpt is a product of Google, and maybe some of you wonder why Google has an OR team. So in the beginning, the OR team started to work on routing problems, really logistic things. So the team was created to work on Google Street View to route the Google Streetcars in a very efficient way. So we ended up creating a logistics solver that's quite flexible, and it's been open source for quite a long time. You can access this on GitHub. It's really the main selling point of ORTools. We also offer this solver as a B2B API under the name of JuMP-dev, Google Maps Platform Route Optimization, which is the core solver plus a few features on the side to help you scale. Nowadays, the team is mostly divided in two sub-teams, so people working on concrete applications, such as workforce scheduling or shipping network design, which are both APIs you can call freely, and people working on lower level solvers, such as Glop, CP-SAT, PDLP. So Glop is an LP solver that's based on the simplex. We have CP-SAT, a CP solver that's using SAT, well, as the name implies. It's quite good, as it won more than 10 gold medals at the Missing competition in the last few years. PDLP is mostly implementation of the first order methods for LP. We also have MathOpt as a modeling layer, so you can use all of these solvers using a unified interface. So it's more or less like MathOptInterface, but well, for other languages. All of this is available as one open source product, which is called ORTools. It's mostly written in C++, but you can access it in Python, Java, and C#, and now a small part of it is available in Julia. And that's really the main part of this presentation. So first, I'll dive into MathOpt, so the equivalent to MathOptInterface in Julia, but within Google. Then I'll spend most of my time to speak about the hurdles that we had in the development and see a bit what the future might bring us about ORTools.jl. But first, here is the life of a model, so that you can see roughly where ORTools.jl will sit. So when you want to solve an optimization model, in a sense, you first model the problem in your head on paper. So you're having some scheduling, some routing problem, and you gather all the data that you need, the decisions that you have to make, what you want to optimize. Then you go to a modeling layer such as JuMP. So you describe your model in such a way that you can give it to a solver in the most user-friendly possible way. And then you have a solver that actually solves the model, and that's where ORTools.jl comes into play. Finally, you retrieve your solution and you do your job with this solution. I'll just briefly show the stack that we are going through before getting to the actual C++ code in ORTools. So here is a least squares model in JuMP. So it's roughly based on what Miles showed yesterday. So it's easy to write. It's the best thing that you can think of as a user to write your optimization model. Internally, it's rewritten as calls to MathOptInterface. So it's much harder to write. But it's lower level. It's something that's much closer to what solvers need to see to solve the models. And then within ORTools.jl, we rewrite this code in a sense to MathOpt, the C++ code. So it roughly does the same thing as MathOptInterface, except it's in C++. It's made for production. It's roughly as fast as MathOptInterface, and it's much more painful to write. But otherwise, it's the same thing. So currently, the core of ORTools.jl is the link between JuMP and MathOpt, which is, as I said, quite close to MathOptInterface.jl. It roughly has the same name, but in practice, it doesn't really work in the same way. So MathOpt is really a C++ library that's hosted in ORTools. It's a modeling layer. And it has quite a few interfaces. So mostly the C++ one that you use to have the best performance. You can also use a protocol buffers interface. So it's really a data-based interface. It's a kind of JSON or XML, but it's binary. I'll dive into the details later on. And that's where we have ORTools.jl. So it wraps this modeling layer in C++ called MathOpt and brings it to MathOptInterface so that you can call all of ORTools' solvers from JuMP. So the main goal is that you have access to CPSAT, to Glop, to PDLP as easily as you can access any other solver. So MathOpt and ORTools in general support quite a few other solvers such as Groby, GLPK, Skip, but in Julia it's not really relevant because you can access all of these solvers using more native packages. But writing this package was not exactly an easy journey. So there are a few keywords that are not really liked in the Julia community. So the first one is C++, because it's not as easy to wrap C++ code as it is for C code. So we decide to bypass this C++ route by using protocol buffers and a very small C interface so that we can jump right into ORTools without having to use C++ from Julia. On the Julia side, that means that we have to use protocol buffers. So there's an existing package that does protocol buffers in Julia, but it's not as easy to use as in other languages. And also, we have a few challenges with MathOptInterface because it's a quite complex interface, but really that was the challenge that we expected in the first place. But the first challenge we really faced is building ORTools from the Julia interface. So in Julia, when you want to build some binary code, you basically use Yggdrasil and Binary Builder for all of your needs so that you get a nice JLL package that users can install. So in principle, everything is good. So Binary Builder uses CMake to build the packages, which is really the de facto standard in the C++ world. So what's nice is that ORTools uses the same compilation infrastructure. But we started to have problems regarding cross-compilation, because ORTools has a lot of CMake code just to cross-compile our code, meaning that we just run the compilation on one typically Linux machine and we target every platform, so that includes Linux, macOS, Windows. It was very well for our needs, but it's really a bespoke infrastructure in the sense that we wrote it over the last few years, and it's not exactly how Yggdrasil and Binary Builder expect the build scripts to be. So the major difference is that to build ORTools, we need to build code generators, especially for protocol buffers. So that means that it's code that must run on the source platform. So if you're building everything from Linux, this code must run on Linux. But still, you're building a lot of code to run on the target platform, which is maybe Windows or macOS. So that means that you have to be quite specific about what you're doing in the script to compile on the right platform. Yeah. Also, there's one difference between Julia and ORTools in the definition of the ARM instruction set. So for Julia, ARM is defined as without the crypto extensions, but some dependencies of ORTools really require these extensions. So that means that it's basically a no-go to use Binary Builder for this use case. The problem is that most people that really run an optimization solver have access to all of these extensions. So we really would like to provide these binaries to ARM users because for the most part, they will be useful to them. So that's why we're currently writing code for using a new solution, which is to use the GLLs whenever we can use the existing infrastructure, because for some platforms it works very well. And otherwise, we'd download the pre-built dependencies that we're publishing on GitHub. Because for ORTools, we're publishing roughly more than 100 binary packages on GitHub. So we'd be reusing all of these packages, including for ARM, with the crypto extensions. So at runtimes, we'd be using the package extension mechanisms to either load the GLLs when it's available or the one that you download directly for GitHub if you cannot use the GLL. The bonus of this design is that we can have ORTools that does not depend on any local binary, which is useful when you're trying to do remote solves. So you're just building your protocol buffers data structure, and you will send them to a remote server for solving your model without doing it locally. So it's some use cases that's useful. Then a bit more about protocol buffers. So at Google, we use protocol buffers for mostly everything. So whenever we have to store some data, it's stored in protocol buffers. When we need to call a function on a remote server, it's protocol buffers. So it's really everywhere. Luckily for us, MathOpt has 3 interfaces. So there's protocol buffers, which is really the pure data interface. So there's really no code involved. You just send a bunch of data to MathOpt using these protocol buffers. So that's how the Java port of MathOpt is implemented. You have a C++ interface that's made really for users. So that's how you can get the best performance when solving your models. And it has the nice feature of not having intermediate data structures. Unlike when you're using protocol buffers, when you're building your whole model as an intermediate data structure, when you're using C++ directly, you don't have that. And during the development of ORTools.jl, there's a new interface that's appeared, which is called Elemental. It's a not so small C API that gives you basically the same features as the C++ code, but a bit more orthogonal. So as it was not really available when we started working on ORTools.jl, we could not use it. But nowadays, it's used for the Python port of MathOpt. So that means that it's still battle-tested code. Then when you go to protocol buffers in Julia, there's that implementation, protobuf.jl. It's community maintained. So that's the opposite of many protocol buffers implementations, which are maintained by Google directly. It also has very few public users. So when you start using the package, you don't know whether it's going to be reliable or not. So we went out and tested the package, and it works quite well for our needs. So it's reliable. The main difficulty was to have the compiler work due to the way it handles path, the dependencies path. But otherwise, well, it works very well. It just has one missing feature, which is mutability. Because we're building the model incrementally, so that means that whenever we add a variable, if we have no mutability, we have to copy the whole model, add its new variable, and serialize it to memory. So that means that it's code that's painful to write, but it's also poor in terms of performance. So the solution we have currently implemented is to duplicate the generated code so we can have that mutability. It's not the way we'd like things to be, so that's why there's a PR pending on protobuf.jl to implement mutability directly into the code generator. Then we're moving up the stack in terms of abstraction and go to MathOptInterface. And here we had the choice of making either an incremental or one-shot interface. So either to have one method to add a variable, a constraint, and so on, or to have a simple copy-to method that copies the whole model into ORTools. So when you go to MathOpt natural C++ API, it works really as the incremental interface of MathOpt. But we're using protocol buffers, so that's not really a point for this decision. When you're starting to write the code, incremental mode in MathOptInterface seems less daunting because you can just split the work into very small chunks that you can work on separately instead of having a whole function to write for copying the model. But more technically, we can really update the underlying data structure when using the incremental mode. So we don't have to perform a copy whenever we're adding a variable and a constraint to resolve the model. So in a sense, it's useful to have this incremental interface. But whenever you're solving a model, as we're using this protocol buffers interface, we have to serialize it in Julia and pass it to the C++ code to deserialize it, which really looks like the one-shot mode in MathOptInterface. Just one more point about the development of this package, because there's a huge mismatch about how Google works and how many languages work, including Julia, and it's about semantic versioning. So Julia packages roughly have to follow semantic versioning in the sense that whenever you have a breaking change, then you have to update your major version. But we're working at Google, and Google works in a monorepo, and we don't really have the notion of version. It's just one single version for every code at Google at once. So that allows us to make huge refactorings really easily, but for external users, well, that's not really a great fit. And breaking changes really happen all the time in our code base, because maybe we'd like to update some API, or there's some automated refactoring that improves performance in all places of the code, but it can break users if you're not updating at the same time. So currently what we're doing is we try to follow semantic versioning in the best way we can, given these constraints, and the fact that there are only few percent really working on the open source code. So we copy the changes from the internal code to the open source product whenever we think we are not going to break too many people. And that means that whenever we have a huge change that we know will break many people, we just wait for a major version to port back these changes. So that means that we can have at some point a huge drift between the internal and external versions of the code. And as the drift increases, then we start to have problems to port new patches into the open source version of ORTools. So for instance, we had a huge refactoring of the routing solver that is lagged behind for more than a year, and we changed a lot of include path and namespaces, class names, and so on. And it's going to be released in the ORTools v10. And yeah, that made quite a lot of problems just to port back things during the year in which this refactoring has been done. So that's all about the feedback that we can give to the Julia community when building ORTools.jl. Now it's time to see what's next for this package. So we know that there are quite a few missing features in the package because we rely on MathOpt internally. That does not give you access to all the features of all solvers. So for instance, for CPSAT, we only have access to the CP model, the integer programming models. We don't have access to the constraint programming part. And it's really a shame because CPSAT is at its core a CP engine. But that's work in progress. We also have problems with PDLP, but it's not in terms of available features, it's just that we have a limitation due to protocol buffers. We only have 2 GB models. And that's quite small for PDLP, which is made for huge models. So in a sense, PDLP starts to be useful at this 2 GB limit. We also want to implement remote solves. Overall, we also need a lot more testing of the code because, well, it's mostly in a prototype shape right now, so you can use it, but we do not guarantee that there won't be bugs everywhere. There's a lot of benchmarking to perform because we're currently using the protocol buffers interface, but we don't know if that's the best choice. Maybe we can have great wins if we re-implement the interface using either elemental or direct C++ code. But for remote solve, we still have to use this protocol buffers interface, so it's gonna stay there. In more details for CPSAT, because we've had quite a lot of feedback from the community that people are really expecting CPSAT in ORTools.jl. So you can already use CPSAT using our JLL, and when you're using the Minisync package. But here we're trying to provide a more direct interface from ORTools.jl that works on all platforms. So currently variables and MY constraints are okay. So that means, for instance, in the CPSAT part that we have all different, that's working. Attributes are mostly implemented. We're working on getting the solver status and solution. So that means that quite soon you should be able to solve IPs and some CPs directly from ORTools.jl with CPSAT. For the next iterations, we'll need to go back to the design stage for more CP constraints, especially those that use interval variables, because it's not really yet supported in MathOptInterface. We also want to support quadratic expressions and callbacks. So that's all for the status update. And there's also a question to you as potential users of ORTools, because ORTools has quite a lot of other solvers and features that are not yet available in Julia, and we don't know how to bring them to Julia in the most useful way. So for instance, we have this huge routing solver for any VRP-like problem that's based on local search. We have a very fast set cover solver that's also based on local search. We have a few bin packing solvers and also graph algorithms. And what's nice about them is that they support DAGs in the sense that they have performance optimizations for them. So a lot of these features are available in other languages, but not all of them in Julia. For graph algorithms, Julia already has a huge ecosystem in terms of graphs, so that's not the most interesting part of ORTools to bring to Julia. But what about the other solvers? So mostly the routing solver, because a lot of people in the academic really like this solver because it works well for their needs. So how would you like to use these features in Julia? So that's all I wanted to say for today.